Okay, we're back. The last video, implicit differentiation part 1, cut me off. So I'm going to finish the problem I was on in video 1, which is the last of example 4. We had gotten the derivative dy dx of our problem, and now we're plugging our point in. So dy dx at the point -1, 2. I'm going to substitute -1 for x and 2 for y. So following this, I'm going to have -2 times my x, which is -1, plus y, which is 2, over -x, that's the opposite of x, so the opposite of my x, which is -1, plus 2 times my y is 2. So that is going to give me a slope of +4 on the top and +5 on the bottom. So this is my slope of the tangent line. Using this slope with this point, I'm now going to write my equation of the tangent line. So using y equals mx plus b, my y value is 2, my slope here is 4/5, my x is -1, and solving for b, I'm going to have 2 equals -4/5 plus b, and when I add 4/5 to the left side, I'm going to get 2 and 4/5. Final answer, equation of the tangent line, y equals 4/5 x plus 2 and 4/5. There we go. And that is example 4. Okay, moving to example 5. This is from our note sheet from yesterday, which looks like this. We're now on example 5. This is asking us to find the second derivative of y with respect to x. You might not have seen this notation before. The 2's indicate that you're taking the derivative of the derivative. That's the second derivative. This could also be notated as y double prime. But because we're in implicit mode, we're going to use the second derivative of y with respect to x. So here we go. Our problem is, I'm going to click and drag this. It's 2x to the third minus 3y squared equals 8. So let's go ahead and use implicit to take the first derivative. Derivative of 2x to the third is going to be 6x squared minus derivative of 3y squared is going to be 6y, tack on dy dx, because it's a y. Derivative of 8 is 0. Solving for dy dx, I'm going to subtract 6x squared from both sides, which is going to give me -6y dy dx equals -6x squared. Divide by -6y on both sides. My final first derivative answer is going to be dy dx equals, look at those -6 cancel, x squared divided by y. This is first derivative. Now, to find second derivative, well, the derivative of dy dx, and watch how this notation comes to life. I love this. If you take the derivative with respect to x of dy dx, meaning I'm taking the derivative of the derivative, I get d times dy. Well, what's d times dy? D to the second y over. What's dx times dx? Dx squared. So there's your notation for second derivative. Now on the right side, when I go to take the derivative of this, I'm going to have to use the quotient rule. So I'm going to use the quotient rule, and remember that anytime I take the derivative of a y, I've got to tack on the dy dx. So here I go. Denominator times derivative of numerator, that's 2x, minus numerator times derivative of denominator. Well, the derivative of y is 1, tack on the dy dx. And this is all over denominator squared. Now here's what's interesting. We do not want to leave dy dx in the answer because we know what dy dx is. dy dx is right here, x squared over y. So I'm going to substitute x squared over y right here. So cleaning this up, I'm going to have 2xy minus x squared times dy dx, which is x squared over y, all over y squared. Using some algebra to move on, I'm going to have 2xy minus x squared times x squared is x to the 4th over y, all over y squared. But now I have a complex fraction, so I think what I'll do to finish this, since I want to get rid of this y right here, I'm going to go ahead and multiply each term by y. So I'm going to multiply this guy by y, this guy by y, and this guy by y. So my final answer, second derivative of y with respect to x, is going to be 2xy squared minus x to the 4th, because these are going to cancel, all over y to the 3rd. And there you have it, second derivative with implicit differentiation.